Hello everyone, welcome to the OneClass channel. My name is Millan, and I'm a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and university or college levels. If you are interested in getting help with your homework, or if you're interested in tutoring, check out the links in the description below. Cool, so to get this physics party started, I'm just going to switch my screens real fast. And let's get this show on the road. Awesome. Okay, so the first question that we have on the menu today is asking us a proton with a speed of 3. Okay, well, what this really means is, I'll write it out. So we're mentioning our proton speed, right? So let's just call that V. P for proton. It's 3.0 times 10 to the power of 5 meters per second. Okay, I'm pretty sure it's really just a formatting issue that's going on with all these spicy looking characters. But okay, so this is our speed. This is the speed of the proton, and it's moving perpendicular to a uniform magnetic field, which is 0.2 teslas. Okay, so let's write that in. Our B field, which is magnetic field, is 0.20 teslas. So this is magnetic field. And this is our proton speed. Okay, and it will follow which type of path? It's going to follow a circular path because we know that charges moving through magnetic fields always follow circular paths, assuming that the charges are moving, that is. And include, we want to find the radius, and then we got some other information like the charge of a proton. So here we have Q. Let's call that QP, charge for a proton. This will be positive 1.6 times 10 to the negative 19 coulombs. So this is a proton charge. And that's just a nice thing that you could memorize. It's not mandatory that you memorize it, but you're going to see this number so often that it really is in your best interest to keep it in the mental reservoir. Okay, so that was given by the question, is the charge of a proton, and we also have the mass of a proton, and that is 1.67 times 10 to the negative 27 kilograms. So let's call that MP. So this is 1.67 times 10 to the negative 27 kilogram. Now, please excuse the formatting here. I'm pretty sure this could be just a technical issue on the UTF encoding. That's really deep into like programming stuff. You don't really need to worry about this, but yeah, so this is the proton mass. And what we're trying to find here is the path of proton travel. And it's asking specifically the radius and radius. Okay, so this is our question. And the first thing that we want to mention is, I'll write this in a different color, maybe purple. Important. This is a rule that we always know about charges moving in magnetic fields. So, charges in magnetic fields always follow circular paths. Okay, now let's think about for a minute, why is this even the case? Okay, so I'm going to scroll down a bit, but all this information up here will still be relevant. We'll come back to that in a moment. But here is the equation for magnetic force. So let's call that FB. Why do we use B for magnets? Just because I think M, like we can't really use M because M is used for mass. So mass and magnets, both using M, that would be confusing. So we're going to use a completely unrelated letter, but it's okay. You just got to get used to it, and it's really not that bad once we get familiar with it. Just remember B typically refers to magnetic fields. Okay, so the magnetic force on a charge is the result of the charge itself multiplied by the cross product of velocity multiplied or cross product with the B field, which is the magnetic field. Okay, so suppose that we have a charge like this. Let's call that Q, and it's going this way. And let's say the B field is going, or this is the V, and let's say the B field is going into the page. Or coming out of the page, that's what I meant. So it's kind of like this dot and X notation means in or out of the page. So dot means out of the page. X means into page. And you can kind of think of it like, you know, we have these arrows, right? And these arrows have their little like quills at the end to help them like be aerodynamic. So into the page, you're kind of looking at the tail end, the quills of an arrow, and out of the page, while you're looking at the tip of the arrow. So in this case, we're looking like this. So if we want to do the cross product here, we want to follow the right-hand rule for cross product. And that essentially is saying like our index fingers are going to go towards the velocity, the first thing that we're cross producting. Our palm is going to go towards the B field. In this case, we're going out of the page. And our thumb is going to be in the direction of the result. So in this case, the result would be down this way. FB. Okay, but just a moment later, that FB is going to cause, draw this in a different color, maybe in lighter blue. So a few moments later, Q is going to be like this, and the velocity will have changed because the velocity has to change. You know, because the force causes the velocity to change. Force causes an acceleration. An acceleration is a change in velocity. The magnitude of the velocity does not change. So if it was originally going at like 100 kilometers per hour, it's still going 100 kilometers per hour. But the direction changes. That's what happens with this magnetic force, okay? So now if we recalculate the magnetic force at this point, at this lighter blue Q, we can see like, assuming like the magnetic field is like all throughout and it's always constant. You always have to assume that the magnetic field is constant for circular motion. So the B field is going to be the same. So we want to curl our, well, we first want to have our fingers follow the velocity, and then have our fingers curl towards like out of the page. That's with the B field, and we could see that our magnetic force is where our thumb is pointing, which is here. Okay, so you can see a different, the direction of magnetic force FB is always perpendicular to velocity and this leads to circular motion. It's kind of like centripetal motion. Like if you ever had maybe a situation like this, let's see if I can get like a wire or something like that. Aha. So this is a patch cord to my guitar. Guitars are really cool. So, you know, if I'm spinning it around here like this, you can see that the acceleration, the reason why, like the tip itself is always going the same velocity as it's flying around here, but the force is going towards the center of the spin to make sure that this is not flying away. And if I were to suddenly let go of this, you it would just keep flying in a tangential path, because once I let go, there's no more centripetal force. And that's what this magnetic field is acting, or this magnetic force is acting as. The magnetic force is acting as a centripetal force. Okay, let me write that in to make that super duper clear. So, magnetic force acts as centripetal force. Okay, so that kind of answers the first part of the question here, is when it's asking us what type of path will this particle, proton more specifically, follow. We know that it has to be a circular path. Okay, and yeah. And in this circular path, we know that the magnetic force is going to be equivalent, or is going to be acting as a centripetal force. Okay, so we want to say this. Okay, well, we can write an equation for that. So magnetic force is equal to a centripetal force. And we can represent that with variables like FB for magnetic and F centripetal or FC for the centripetal force. Awesome. Now let's rewrite them in terms of what they're made of. So we know that FB is going to be Q VB. Since we don't really need to worry about the cross product nature of it right now, we can kind of treat it as a multiplication, because we don't have like directions to worry about. But if you want to be more formal, just know that you're going to want to use the cross product unless you're doing like a 2D scalar analysis or a complete scalar analysis. Okay, so we have Q VB, which is equal to the centripetal force. And as we know, the centripetal force is mass times velocity squared over radius. Okay, now, so we know that it's going to be a circular path, and it's asking us to pretty much get the radius of the circular path, because a circle is perfectly defined with just one thing. If you have the radius, you can define the circle. Okay, so let's do some quick algebra to isolate the radius r. Isolate r, or isolate radius r. And let's do it like this. So we can multiply both sides by r and get r on the upstairs, and divide both sides by QVB. So we can have something like this. R equals mv squared over, oh, that v is kind of sketchy looking. Let's redraw that. V squared over QVB. Now, with some quick algebra, we can see that the v on the downstairs neutralizes the v squared, so it just becomes a regular v on the upstairs. So to rewrite this, this is really just mass times velocity over charge times magnetic field. All right, so now we can just substitute in our numbers, and we can call it a day on the radius. Okay, so we got our radius here. What's our m value? We know that it was the mass of a proton, so that's 1.67 times 10 to the negative 27 kilogram. Okay, awesome. Now we have just our velocity, and our velocity is 3.0 times 10 to the 5 meters per second. That is extremely fast, but that is reasonable to expect extremely fast moving protons, because well, in general, they do move quite fast. Because their mass is so low, we do expect them to be moving quite quickly. So don't be alarmed by these large numbers. And it's good to kind of have like a good number sense to know, like, hey, I expect to see a certain degree of magnitude, like maybe 5, 6, 8 you probably wouldn't see, but the 4, 5, or 6 for the power of velocity seems reasonable. Okay, now on the downstairs we got the Q value, and we know that it's going to be the charge of a proton, so that's going to be 1.6 times 10 to the negative 19 coulombs, named after Coulomb. He was a pretty smart guy. And the last thing is B, which is our magnetic field magnitude. So that is 0.2 or 0.20 Teslas, named after Nikola Tesla, not named after the car. Okay, so we would just need to calculate this ASAP fast. Let me just grab my calculator. Boom. My TI-84 calculator. It's an excellent calculator if you're doing some advanced math. So let's calculate this whole thing. 1.67 times 10 to the power negative 27 multiplied by 3 multiplied by 10 to the power of 5 and divide that whole thing by 1.6 times 10 to the power of negative 19 multiplied by 0.2. And the result I got for that hopefully matches with this one. It does. So the result I had for this is 0.0156565 meters, which seems reasonable. And now let's do a significant figures analysis. So we know that everything was given with like all of our component numbers are 2 or 3 significant figures, so we have to give it to 2 significant figures. So to 2 significant figs, 2 SF, R is equal to 0.016 meters. Another way you could write that is 1.6 centimeters. That is a radius maybe about the size of maybe like a piece of corn. So that'd be like the radius of this circular path, about the size of a piece of corn, 1.6 centimeters. Pretty small, but pretty good. So yeah, the above solution. So it seems that we got the solution good here. Solution is good. Watch out for sig figs and mention of how charged particles moving in P fields follow circular path, and that centripetal equals magnetic force would be good. Cool. That was fun. Okay, so the next question that we got on the menu today is asking us, a spring has a constant force constant, or a spring has a force constant of 147 newtons per meter and an unstretched length of 5 centimeters. On one end of the spring, I'm guessing, is attached to a post that is free to rotate in the center of a smooth table, as shown in the top view diagram. The other end of the spring is attached to a 7 kilogram disc moving in a uniform circular motion on the table. And it stretches the internal string by 2 centimeters. There's no friction, so that's nice. So it's going to ask, the first question is asking us is, what is the centripetal force of the disc? Answer in newtons. And what is the work done on the disc by the spring doing one full circle? Okay, so let's go back to the question and extract our information of interest. Okay, so the first thing that we got going on is the spring has a force constant of 147 newtons per meter. Okay, so let's call that K. Typically K is what you use to represent a spring constant. So let's call that Ks for constant spring. We don't use C because C is used for the speed of light as well for charge, so we don't want to be too confusing, so we use K. And we know that we have 147 newtons per meter. Okay, now we also have the unstretched length. Let's call that x0. Okay, so this is, let's actually write out what these are. So this is spring constant. And our unstretched length, 5 centimeters. So let's write that instead as 5 times, or instead 5 centimeters, which is equal to 0.05 meters. So this is unstretched length. Now it's good to convert all of your given numbers into base SI. It will make your calculations a lot easier. Otherwise, you need to deal with like the centi prefix and like milli prefixes. Those prefixes are uncomfortable to deal with, but you got to do what you got to do. So yeah, this is what I would recommend. And the stretched length is 7 centimeters. So let's call that XS or X long is 7 centimeters, and that is 0.07 meters stretched length. Length total. And for the change in x, this is going to be important because for when we do the force calculation, this is just going to be x long minus x naught or xo, and this will be 0.07 centimeters, oops, not centimeters, regular meters, minus 0.05 meters, and this is equal to 0.02 meters, and this is stretched length. Okay, and the last thing that we need to know is that the disk is 7 kilograms. So let's call that MD, D for disk, and that is 7 kilograms, kg. So these are all of our important things that we need to know. Okay, so the first question is asking us, what is the centripetal force on the disk? Now, the centripetal force is what causes the disk to stay in its circular path. If that centripetal force were to suddenly disappear, the disk would immediately stop following the circular path and would just keep following the current direction that it was following. So, yeah, so the centripetal force in this case all comes from the spring. Okay, so I'll write that in a different color. F centripetal is equal to F spring. And we know this because, well, look, just looking at the diagram, there's nothing else that could really give us any forces. So nothing else to contribute to forces. Okay, now let's now that we know that the centripetal force is completely made up of the spring force, we just need to calculate the spring force. So we know the spring force, F spring, is equal to the Ks, the spring constant, multiplied by the distance or the change in distance of the spring, or the change in length of the spring from its original length. So that's why we had to get the delta x value. Delta means the change in x. So let's actually get this calculation real fast. Should be pretty straightforward. So we know that our spring constant is 147 Newton times meters, or Newton divided meters, my bad. And we had 0.02 meters on the like how far the change in length of the spring between its natural length and its stretched length. So we can run this calculation ASAP fast. 147 multiplied 0.02, and we get 2.94 newtons. And you can kind of see how the meters on the length neutralizes the meters in newtons per meter. So the units definitely work out. And we come to the same conclusion here. Awesome, yeah. So the centripetal force is this, 2.94 meters, because we know that the spring is who's supplying the centripetal force. And if we really wanted to, we could calculate how fast it's traveling, but the question didn't ask for it, so don't necessarily need to, we don't need to calculate things that are not asked for us. It's typically not a great investment of time, especially on your tests where time can be quite tight. Okay, so this will be centripetal force. Centripetal force on disk. Okay, so the next part of the question is, what is the work done on the disk by the spring after an entire circle is done? Now, this is a situation where we want to bring up one of our important rules about work. Work has to have the force and the displacement be in the same direction. Or must be parallel. Only the parallel force and displacement components count or contribute to the work. So an example of me doing work is, or an example of work happening is if I drop something. Gravity is putting the force downwards and the displacement is downwards. Gravity is doing work in that scenario, but me pushing something perfectly horizontally, that's also work. That's work done from me because my force is putting it horizontally and it's moving horizontally, but gravity is not doing any work when I'm doing that because gravity's force is completely downwards and its displacement is horizontal, so they're perpendicular, so there's no contribution of gravity on the work. In that situation of me pushing like a shopping cart, that's only going to be me doing the work. Gravity's doing no work because gravity is perpendicular to the motion. Now let's think about this situation real fast. Okay, so at any given point on the circular motion, given point along the circular motion, the centripetal force is perpendicular to velocity and its recent displacement and its displacement, I guess. Okay, so let's draw a circle real fast using Paint's beautiful tools. Okay, so suppose, let's do this in red. Yeah, red circle, that's cool. And we can get a black pen. So at this moment right here, our velocity and displacement are this way, and our centripetal force is this way. They're perpendicular, no work. No work, perpendicular. Okay, and on maybe right here, we have a similar story going on. So the FC is going towards the center, and the velocity is going this way. So we have another situation just like that. There's no work. The force and the velocity are perpendicular to each other, meaning the force and how it's moving in response to that force are perpendicular to each other. There cannot be any work done as a result of that, which means that the only possible thing here is that the work is 0 joules. Okay, so just remember to keep this in mind. I like to use that shopping cart example. Like when I'm pushing the shopping cart, gravity's doing no work. It's all me doing the work because gravity is going perpendicular to its motion. Okay, so that similar concept applies here, and we can see fairly clearly that there's going to be no work done because the perpendicularness. Okay, so yeah, the above solution is good. Mention of how the centripetal force is facilitated by the spring only would be good. Cool. Okay, so the next question that we got on the menu today is looks a little shocking, but I'm sure that we can electrify our way through this. Okay, so we have 3 identical light bulbs. It's good to know that they're identical. That will probably be important later. Okay, so we have 3 identical light bulbs that are connected to 2 batteries that are shown just like this. Okay, so to start the analysis of the circuit, we got to write loop equations or energy conservation equations. And each equation must involve a round-trip path that begins and ends at the same location. That's kind of the definition of a loop equation, but it's nice to have that specified. So each segment of the path should go through a wire, a bulb, or a battery, not through the air. How many valid loops can we write for this circuit? Okay, so this really gets into like loop analysis, and this subject can go really deep, especially if you're trying to get into like electrical engineering. Those of you who are interested in electrical engineering, this will be a quite common sight in your future career path. Okay, so let's actually redraw the circuit more in terms of what you would typically see for electrical circuits, especially as you go deeper into like science or into electrical engineering. Okay, so we know that we have 3 identical resistors, or these lights, we can pretty much draw them as resistors. Okay, because they really just, if current goes through them, they turn on and they dissipate some energy, but they don't store any energy, so they're not like any storage elements. I guess a lot deeper into like electrical engineering stuff, but it's kind of out of the scheme of this question. So, and we know that they're identical, so we could just give them resistor values of capital R, and we know that they're all going to be the same, so we can treat that capital R as the same for any one. Okay, so we have 2 of them in parallel, and those 2 in parallel are in series with another one, like this. And we have 2 batteries like this. I like drawing batteries like this. Sometimes you'll see people drawing batteries like this, but this can get very confusing when you get deeper into your electricity world, because you're going to see capacitors which look fairly similar to that. So I'd recommend you stick into these like circles with the plus minus inside. Okay, so we have 2 batteries in a series like that, and we want to write some equations for this, or some loops. So let's give some names to these batteries. So let's call this B1 and B2, and they can have an associated voltage with them, because we'll treat them as voltage sources. So we can call this maybe instead of B we can use V instead for voltage. Sometimes people also use E for electromotive force, but V is going to be the most common, especially in like electrical engineering. I'm not really in electrical engineering myself, more in the software world, but there's a lot of overlap, and a lot of my friends are in electrical engineering and share a lot of knowledge. Okay, so how many valid loop equations could we make for this? Let's draw them out. So the first one, as we can make in this blue color, we could see that this will go, actually, instead of drawing this, because this is going to get quite messy, let's give this like let's give our R values numbers, R1, R2, R3, and we can just write like the components that we'll see along the road. Okay, so let's say our first loop, we can go like the most outside loop. So this can be V2 to V1 to R1 to R2 to back to V2, and that'll be one loop. Okay, and if you kind of draw it out like, or draw out like loops like this, it can be very clear in terms of what elements you're doing, and it's pretty easy to follow. Okay, now what if we do the same thing, except instead of R2, we do an R3. Okay, that can be a quick copy pasta. So this would be another perfectly legitimate and reasonable loop. Do an R3 instead of R2, and another loop that we can do is just R2 and R3. Right? You can see that this is like a loop, and that'd be a perfectly valid loop to use as well. Valid, not necessarily useful, but certainly valid. Okay, so yeah, R2 to R3 to R2 again. Okay. Yeah, so these would be some of our, or we could also possibly do another loop if we were to compress all of these resistors into a single resistor, but since I have a feeling this question is trying to keep us to, is trying to have us keep the original circuit, so these would be our possible loops. Possible loops, and this gets very useful for Kirchhoff's voltage rule. Okay, so keep that in mind. Kirchhoff's voltage rule. Yeah, or I think it's law instead of rule, but same thing. Okay, so E1 refers to the electric filament in bulb 1. We don't really need L because we're based on Kirchhoff's voltage law. So we know that Kirchhoff's voltage law or rule is as follows. We know that the sum of all voltages in a loop is 0. Okay, so this question's something a little bit fishy about this question is they have E. I guess if E represents the electric field instead of voltage, this could kind of work out, but we need some more context about like the internal information about the light, but we can still proceed. So is small enough to neglect. Okay, for the connecting wires, that's cool. So which one of these would be legitimate loops? So EMFs those are going to refer to the batteries. So the batteries, and then -1 and then -3. So that's one of them. So that's identified. I guess it's kind of like a multiple choice type situation that we got here. Then we have 1 and 2. Assuming this is 1 and 2, that would not make a legitimate loop. So that's disqualified. And then this one, subbing out 2 instead of 3, that's a perfectly legitimate one. So hopefully you can see that highlight. Okay, you can. So this one, that's good. And this one is good. And our last one is just going to be R2, R3, and then back to R2. But we're not going to write R2 twice. We're going to put put them in just once. And that corresponds to this one, and they're going to have opposite signs because you do need to take into account that you're going to go through one of the resistors backwards, which is going to translate to a negative voltage. Okay, cool. So for our final answer, it would be this one, this one, and this one. We can make corresponding KVL or Kirchhoff voltage rule, Kirchhoff voltage law equations to correspond to that. Okay, cool. So it's also so I guess this is another part of the question is asking us. It's also necessary to write charge conservation equations for the node equations, which corresponds to Kirchhoff's current law. So that let me write out what Kirchhoff's current law is real fast. It's law, not bad. So Kirchhoff was a pretty smart scientist who named these things. Whoops, not circuits, current. Commonly known as KCL, and this is commonly known as KVL. Sum of all currents in a node is 0. Or another way that you could write this is the sum of incoming currents is equal to the sum of outgoing currents. I prefer to write it this way because otherwise you need to set a standard for if negative current is incoming or negative current is outgoing, and it doesn't matter which one you choose, which can really make it quite confusing. So I would recommend that you do the sum of the incoming on one side of the equals and the sum of the outgoing on the other side of the equals, and that way you will always have you won't need to worry about those like sign conventions as much. Okay, so let's actually write out what these are. Let's say this corresponds to this branch here. Let's say that corresponds to I1, current 1, and I2, and I3. So the current numbers correspond to the resistors that they flow through. And so which one of these are valid? So the node of interest is the node right here. So let's call that node A, and I'll redraw that down here. So node A, I named it A. It's not formally known as A, but here we have R1, R2, R3, and the rest of the circuit we don't really need to draw. It's not really relevant. We just need to look at this particular node and the things connected to this particular node. So, given at node A, let's use this KCL equation. What is the incoming currents? Who's incoming to node A? I1, well that's incoming to node A, so we can write that on the left side, I1. And is there anyone else incoming? I2, well that seems to be leaving node A, and our I3 also seems to be leaving the node. So on the other side of this, we could do I2 plus I3. And this would be our equation of that multiple choice situation, I'm guessing, right here. So I1 equals I2 plus I3. That's the one. That's the one that we want to use because we need to consider Kirchhoff's current law and know that the incoming currents is equal to all of the outgoing currents added together. And in this case, we only got one incoming and we got two outcoming, so or outgoing. So you know this would be the only one that matches with that. So the only way that like I1 could be equal to I3 is if I2 was 0, and that would only be the case if like R2 was so absurdly high that it's pretty much like not connected. So that'd be the only case that happens, and vice versa for I1 equals I2. So KCL, Kirchhoff current law. That's the real key to this one. Okay, cool. Okay. So for the next part of this question, It's asking us, or it's giving us this information first. Each battery has a voltage, EMF means voltage, of 1.4 volts. The length of the filament in each bulb is 0.013 meters, and the radius of each filament is 5 micrometers, quite slim. And the electron mobility is 1.8 or times 10 to the negative 3 meters per second per volt per meter. And tungsten has quite a few mobile electrons per cubic meter. Okay, now given these quantities, we want to get essentially what we're looking for, given all of this information, is the magnitude of the electric field inside of each one of these bulbs, and the current that goes through each one of these bulbs, which is pretty much we just want to find the voltage that goes through each one of these resistors, as well as the resistance through each one of these resistors, because we know that once we have the voltage of a bulb, this voltage of a bulb is going to be equal to the electric field inside multiplied by the length of the filament. And we know the length of the filament, so once we get the voltage, we can just divide the length of the filament to get the electric field. Okay, so, but first, what we really need is the resistance that corresponds to each one of these light bulbs. Okay, so that's what we want to find first. Okay, resistance of the light bulbs. Okay, so what have we been given here? So far we've been given the length of the filament. So let's call that L, cursive L. This is 0.013 meters. Our radius of the filament, let's call our radius R. Let's call that radius is going to be 5 times 10 to the negative 6 meters. Very slim. Electron mobility of tungsten, let's represent that with mu. So the electron mobility is 1.8 times 10 to the negative 3 meters per second per volts per meters. That's a spicy unit. And tungsten has a number of electrons. Let's represent that with N. That's going to be 6 times 10 to the 28 electrons per cubic meter. Okay, the first thing that we're going to want to do is we want to find the conductance of this. So the conductance is equal to, well, we'll represent it with the Greek letter omega, lowercase omega, or sigma, my bad. And this is going to be our N value, which is our number of electrons per cubic meter, multiplied by our electron mobility, my bad, and multiply that by the charge of an electron. So this is, I'll just write in what these are, length of filament, radius of filament, this is electron mobility, and this is electron density. Okay, so if we math this out, we know that we're going to have 6 times 10 to the 28. Let's not really worry about the units, because these are going to get quite messy if we did 1.8 times 10 to the negative 3. And we have to multiply that whole thing by the charge of an electron. So 1.6 times 10 to the negative 19. Okay, and our calculation for this is going to be 17280. Okay, and that is going to be our conductance value. So given our conductance value, we want to use this in Poilet's law to get the resistance. So we know that resistance is equal to rho, and I'll explain what rho is real fast. Actually, instead of writing rho, I'll just write it in terms of conductance. So we're gonna have the length over the conductance times A. A is the cross-sectional area of the filament. So to represent that, we will substitute out, we're going to assume that it's going to be circular. So we're going to do like this. L over conductance times pi r squared. Okay, so let's substitute in our numbers. Our L value was 0.013. Our rho value, or I mean our sigma value, is 1728000. Multiply that by pi. Multiply that by the radius, which is 5 times 10 to the negative 6. And we got to square that thing off. Okay, and our R result for this is going to be something like this. So the point 0.013 divide by 1728000 times pi times, in brackets, 5 times 10 to the power of negative 6 squared. And the result of this is 9.58 ohms, which is reasonable. Okay, so this is the resistance of one light. Now, given this, we can redraw our circuit to match that. Whoops. Let me clear out the bottom here. It's unrelated to a different question. My bad. Okay, so let's redraw the circuit ASAP fast. So we have plus minus 2.8 volts. Oops, not R1. R. I know that all of them are 9.58 ohms. Okay, so let's combine this into a single resistor. So to get the equivalent resistance of this entire circuit, we're going to have something like this. So Req is equal to R plus 1 over R plus 1 over R to the negative 1. So as you can see, we have two parallel resistors, and those two parallels are in series with another one. So with some quick math, we know that in parallel, these are identical. Identical resistors in parallel have an equivalent that is exactly half. So we're going to have 1/2 of R for these two, and then plus R. So we're just going to have 3/2 of R, so 1.5 R. Yeah, do the math real fast, and you'll believe me, and you'll come to the same result. So subbing in R is equal to 9.58 ohms. We know that Req is equal to 1.5 times 9.58. Here we have 14.37 ohms. And assuming that here is like I1, here we have I2 and I3 going through those corresponding branches. I2, I3. We'll have this system, and so we know that I1. This is from Ohm's law. I1 is equal to the V over REQ. V is 2.8 volts. REQ is 14.37 ohms. And doing this math real fast is that times 2.8 is, this corresponds to 0.195 amps. Okay, so that was like one of the things that we're asking for, is asking for the current going through them. And since we know that I2 and I3 added together have to be equal to I1, we know that the branches I2 and I3 are equivalent, like the resistor on those paths are the same. We know that 1/2 of I1 is going to go down I2 and 1/2 is going to be I3. So I2 is equal to 1/2 I1. So equivalent, valent, parallel paths. So this is going to be equal to 0.5 times 0.195 amps. This is going to be 0.097 amps. Okay, so this gives us I1 and I2, and I3 is going to be equal to I2. And this will give us exactly what we need for there. And then once we have this, we can use Ohm's law again. V equals, or let's say V1 is corresponding to I1 times R. And this will be equal to, I1 is going to be 0.195 amps. R is going to be 9.58 ohms. And the voltage for that is going to be times 9.58 is 1.87 volts. And this is going to be equal to our electric field multiplied by 0.013 meters, because that's the length of the filament. We know that from way up there we had resistance of the bulb, or no, the voltage of the bulb is equal to the electric field inside multiplied by the length of the filament. So given that, we can isolate the E, which is just going to be 1.87 divided by 0.013. And that's going to give us an electric field that corresponds to 143.59 newtons per coulomb. So this is for E1. And for V2, we're going to do the same thing, except we're going to have a different current value. So I2 for R, so this is going to be 0.097A multiplied by 9.58 ohms. This is going to be exactly half of the voltage that we had up there. Yeah, so 1.87 divided 2 is 0.935 volts, and this is also equal, well, that was E1, this is equal to E2 times 0.013 meters. And then isolating for E2, we're going to have that divided by 0.013. And here we're going to have 71.92 newtons per coulomb for the electric field in the second light bulb. Okay, so we got the currents, we got the electric field inside, and that pretty much concludes everything that we need to know about this question. I know it's been an extremely long question, but we got to do what we got to do. You know, sometimes your exams will be this long, and you got to stay focused and just stay sharp and yeah, stay good. So there is no above solution. Yikes. Okay, so there's no solution to verify. Okay. Okay, so the next question that we got on the menu today is asking us, a monoatomic ideal gas is held in a thermally insulated container with a volume of almost 10% of a cubic meter. The pressure of the gas is 115 kilopascals and its temperature is 325 Kelvin. What volume of the gas must be, or how much should we compress the gas to what volume until we get its pressure up to 185? And we're going to assume that the temperature is constant. And at what volume of gas will the temperature have? At what volume will the gas have a temperature of 279 Kelvin? At 2 cubic meters. I think that might be the answer that they're giving us. But okay, let's do this question and let's figure out. Let's do the physics. So the key word that we want to see here is ideal gas. And as we all know, our ideal gas law. Let's write that out. Is PV equals nRT. Okay, P is going to be pressure. V is volume. N is number of moles. R is the Rydberg constant. And T is Kelvin. I mean, not Kelvin, is temperature in Kelvin. Okay, so what we know is that our P, our V, and our T are going to be variable. And let's do a different color like blue. And these are going to be constants. And how do we know that we're constant? Well, the Rydberg constant, it has to be a constant. But for the number of moles, it's in a thermally isolated container. And you can't be thermally isolated unless you are isolated in terms of volume as well. So like you can't be adding in new things into there. Okay, so let's isolate all the constants. And then with the variables, they should like match up with each other. Yeah, so first thing that we're going to want to do is isolate the constants. So we have just N and R, so we just have PV over T is equal to NR. And we're going to change these. So let's actually say we can have like pressure 1, volume 1, temperature 1 is equal to pressure 2, volume 2, and temperature 2. So temperature 2 can be like what we have finally, and the 1 values corresponds to what we have originally. So let's actually write out these values. So our first pressure, P1, that was given to us as 115 kilopascals. Kilopascals. Oops, I completely messed it up. Kilopascals. Our volume 1 is going to be 0.0930 meters cubed, and the temperature was 325 Kelvin. 25 Kelvin. Okay, now to what volume must the gas be compressed to increase its pressure to 185? Okay, so this will give us P2, 185 kilopascals. And we're going to assume that the temperature is going to be the same because it didn't say that we're going to change the temperature. So it seems that we're just reducing the volume to increase the pressure. Okay, so we're solving for the volume. So given this relationship here, let's solve for V2. So V2, we don't know that. So we want to solve for V2, and that will be P1 V1 over T1 multiplied by T2 over P2. Since T1 and T2 are equal, we can neutralize them out of the equation. Okay, so V2 is just going to be P1, so that's 115 kilopascals, multiplied by V1, that is 0.0930 meters cubed, divided by the second pressure, which is 185 kilopascals. All right, let's ask our handy dandy calculator to get the answer for us. 115 times 0.093 divided by 185. And that gives us a result of V2 is equal to 0.05781 meters cubed. And this makes sense because if we increase the pressure, that means we have to reduce the volume, and the volume is smaller than it was originally. So this is going to be our brand new volume value. Okay, so that will be our result here. Cool. And we got the same thing? Yes, we did. So that's awesome. And then our second question is asking us, what volume will the gas have a temperature of 279 Kelvin? We would kind of need to, let's assume that the pressure is going to stay the same. So for part 2, we want to find volume. Oh, I think this is kind of related to the first one, except we're not going to have T1 equal T2 anymore. Okay, so for problem 2, or instead of P2, I'll write Q2. So this is going to be the same relationship, except we're going to have T2 is not equal to T1. So T1 was 325. And T2 is 279. And everything else is going to be the same. So the V2 here is going to be the same, except we're going to uncancel these, the T1 and the T2 terms. So we're going to have V2 is equal to P1 V1 over P2 times T2 over T1. So let's call this V22 because it's like the V2 of the second volume corresponding to the second equation. Okay, so it's pretty much just the same as the previous. So let's just rewrite that. V22 is equal to 115 kilopascals multiplied by 0.0930 cubic meters, 185 kilopascals, multiplied by T2, which is 279 Kelvin, over 325 Kelvin. Okay, so we can just really take our previous answer. Yep, so we take our previous answer multiplied by 279 divided by 325. And the result that I calculated was V22 is equal to 0.0496 cubic meters. Okay, so this would be the results for our question here. Sounds good. And we calculate the same thing, 496. Sounds awesome. So, yep, we kind of did need to come to the conclusion that our temperature was increasing between the changes from the initial to the final. I'm very confused as to why it has 2 cubic meters. Not really sure what that corresponds to, but you know, it's important to sometimes you'll get information in a question that is not relevant. Okay, so the above solution is good. Would be better to show the process with part 2 where the 2 temperature values are incorporated. Cool. Okay, so the next question that we got on the menu today is asking us, in order to be able to determine her speed, a skydiver carries a tone generator, which is pretty much just a speaker. A friend on the ground at the landing site has equipment for receiving and analyzing sound waves. While the skydiver is falling at terminal speed, that means she is not increasing her speed, but that means her speed is constant as she's falling. Her tone generator emits a steady tone of 1480 hertz. You can probably hear that. That might sound like a bass guitar or something like that. Assume the air is calm and that the speed of sound is 343 meters per second, independent of altitude. That's important because the speed of sound actually depends on the air pressure, but we're going to ignore that. And we're just going to use 343 for all across the board. If a friend was on the ground and receives waves at a higher frequency of 3,260 hertz instead of, which is higher than the original that she's doing, what is the skydiver's speed of descent? Answer in meters per second. And if the skydiver was carrying equipment so if the skydiver is emitting sounds and also has a receiver, what would be the frequency of the sound that she receives? This is a very fascinating question. So the most important part of this question here is that we're dealing with the consequence of the Doppler effect, right? Doppler effect. So this is what pretty much the Doppler effect is. Higher frequencies when approaching lower frequencies when I guess the opposite of approaching is leaving. Okay, so let's actually think about this. You ever seen, like, I know in cartoons when people like drop things, it's like it's kind of like that's as the thing is going away from you, as it's falling, it's like, you know, the pitch is going down. So like as it's getting farther away from you, the frequencies are getting lower as they're approaching you. Okay, so that's like kind of maybe how you see the Doppler effect in you know, in like cartoons and stuff. But what's really happening is, like, let's say you have like a dot right here and you're having just regular waves and they're going out at a certain frequency, right? So, you know, this is like your regular wavelength. So as it's approaching you, like this, you know, it makes the wave here, but they kind of get a lot, like the wavelengths get a lot closer together because you're moving in proportion to the wave. Like you set out a sound. If I'm moving with the sound, like it's going to get higher frequencies. So this area is like compression. Leads to higher frequencies. And if you're on the other side, let's put this in a different color. If you're on the blue side here, you can see that like the waves are like spreading out because I'm moving and I'm producing new waves in a different position than the previous. That this kind of going to contribute to the change in the wavelength. So spread, and this leads to lower frequencies. Okay, cool. So let's extract some of our given information and then try to calculate what's going on, because there are some nice Doppler effect equations that can definitely help us come to a conclusion here. Okay, so we have a skydiver terminal. So our velocity is going to be constant, which is nice. And we know that the tone generator, so the F source, I think they use F source, right? Yeah, so I use FE, but we can use F source. This is 1480 hertz. So the F ground, that's going to be, that was given as 3,260. So the V sound was given as 343 meters per second. And we need to now solve for the velocity of the diver. Solve for. Okay, cool. So what we're going to do here is we're going to use our Doppler equation, which looks like this. Doppler equation for approaches, or for approaching objects. Okay, so here's the equation for the Doppler effect with approaching objects. We have the frequency as observed by the observer. So let's call that F ground, because in this case the observer is on the ground. And we know that it's going to be the same as the F source, but the F source needs to be scaled. And the amount that it's scaled by is the sum of the velocity of sound over the velocity of sound minus the velocity of the diver. Now, if we were like perhaps in the airplane above, and this would be plus instead. So when it's approaching, we have negative, or we have a minus in the denominator. If it's something that's getting away from us, it's a positive in the denominator. Okay, so this is, let's isolate, we have to isolate F diver, and that will give us exactly what we need. So first, let's bring the F's to the same side. So we have FG, G for ground, just to make this a little bit shorter to write, and then VSOS, speed of sound, SOS, VSOS minus VD. Okay, then we're going to multiply both sides by the denominator of the right side here. And we can put the reciprocal of FG, FS to the other side. So we're going to have VSOS minus VD is equal to F of S over F of G, VSOS. And now to isolate VD, we will do VSOS minus FS over FG, VSOS. And then we can factor out the VSOS from the right side. So we can have VD is equal to VSOS multiplied by 1 minus FS over FG. Now, we were given all the numbers that we need for this, so how about we just sub them in and we can calculate the numbers or the result for the velocity of the diver. So the VSOS, that was 343 meters per second. Here we have 1 minus, now what was the source? The source was 1480 hertz. So 1480 hertz over 3260 hertz. Okay, now we send that through my calculator and we can see what we get. Cool. So the result that I calculated was VD is equal to 187.28 meters per second. Okay, seems like a reasonable calculation. It seems that the given solution here agrees with us, but this calculation is a little bit wonky, so we gotta watch out for that. And now for what the receiver hears, or what the diver hears. So essentially what is heard at the ground is like directly reflected back up. And you know, now it's a situation where we want to see the Doppler effect again, but on the reflected wave. So the source in this case, so for part 2, the reflected wave. We know that in this case, the source is the ground. So the frequency of the source in this case is, well, it'd be the same as what the ground was hearing originally, which was 3260 hertz. Okay, the velocity of sound, VSOS, is going to be the same, so 343 meters per second. And we know that the person is falling at 187, so V diver is equal to 187.28 meters per second. Now we're going to be pretty much using the same equation as before, because even though the source is like not moving, actually my bad, the source is not moving, it's the observer that's moving. So the more formal equation for the Doppler effect for a stationary source so here's the general equation. It looks as followed. Okay, so we have F observed is equal to the F's of the source times the velocity of sound plus the velocity of the observer and then this is over the VSOS, the speed of sound, minus plus the velocity of the source. Okay. So it's minus for when we're approaching, and plus for when we are, you know, getting farther away from it. But in this case, the source is the ground, and does not move. Zeroes out. Okay, so essentially we just have to sub in the equation. So the observed we don't really need to do any algebra because it's already organized in the proper way. So we have F observed is equal to Fs for F source, and then VSOS plus VD, the diver is the observer in this case, all over the VSOS. And I guess we can do minus 0 because the source is not moving, but you know, we don't really need to write that. And let's sub in our numbers and figure this thing out. is equal to, the source in this case is the reflected signal off of the ground. So it's immediately after it was reflected off the ground, it was 3260 hertz, multiplied by the speed of sound, which is, or the fraction of 343 meters per second, plus 187.28 meters per second, all over 343 meters per second. Okay, now I was sending this to my calculator to figure what this is. 3260 multiplied by the fraction of 343 plus 187.28 all over 343. The results of this I expect to be higher than its original, and in this case we found it to be 5040 hertz. Just about. Like, we're rounding a little bit here, but yeah, that's we're going to hear a much higher frequency, and it seems that the calculation here agrees with us. So the above solution is it's mostly good. So the fraction to find velocity diver is wrong. The shown should be flipped because the calculation as is would lead to a negative result. Cool. Okay, so the next question that we have on the menu today is asking us to find the equivalent capacitance of the circuit. Answer in, I'm going to assume microfarads because everything else is given in microfarads, and then we got to determine the charge on this capacitor right here. Okay, so there are a couple of rules for finding equivalent capacitance. In parallel, they're very easy. You just add them up normally. So to write this formally in math terms, we have the equivalent capacitance is just the sum of the component capacitances. Now, if we're in series capacitors, is kind of similar to what you would do with parallel resistors. So 1 over... You have to add up the reciprocals of all the components and then take the reciprocal of that result. Okay, so that would be how you find the series capacitor values. Okay, so let's draw out this circuit, or just really draw out the capacitors, because that's what's really important. So here we have 1.41 microfarads, and then we have a little parallel branch where we have 4.63 microfarads on top, and then we also have 3.24 microfarads on the bottom. And then here, kind of looks like a source, but we're going to treat it as a capacitor because it says 7.96 microfarads. Okay, and we're looking for the CEQ across here. So the first thing that we want to see is, hey, don't we got a parallel section right there? Wouldn't that be nice and easy to compress? So we know that this CEQ for this section is going to be 3.24 microfarads plus 4.63 microfarads, which is equal to 787 microfarads. Okay, so we can redraw the circuit as 1.41, 7.87, 7.96 microfarads, Okay, and now we have 3 in parallel. I mean 3 in series. So we can find the equivalent like this. CEQ is equal to 1 over 1.41 microfarads plus 1 over 7.87 microfarads plus 1 over 7.96 microfarads. That whole thing to the power of -1. And let's run that through the calculator and figure out what it is. So we got 1.41, 7.87, 7.96, all reciprocaled, and my final result was 1.04 microfarads. This shall be the equivalent capacitance of the circuit. Cool. Now we want to determine the charge on the 141 or the 1.41 capacitor. And that's fairly simple because we know that the charge on series capacitors is always the same for all of them. Okay, so that's going to be a nice rule to keep in mind. All series capacitors have the same charge. On them. Okay, so we know across this whole thing, we can kind of redraw the circuit as so. So we have a 10-volt source. And here we have just CEQ, which corresponds to 1.04 microfarads. Okay, so we know that the 1.41 is in series with all the other ones. So if we find the charge for the equivalent capacitance of all of them, we know that like one of the series components that originally made it up has to have the same charge on it. Okay, and we know that the charge, the capacitor equation of interest is going to be Q equals CV. So that's capacitance, and this is voltage. So hopefully it should be fairly obvious that the voltage across the entire equivalent capacitor network is 10 volts. So we will have V is equal to 10 volts, and C is equal to CEQ, which in this case is 1.04, I believe, microfarads. So we had, right? 1.04, yep. So we multiply them together, and we can get the charge on it. So Q is equal to 1.04 microfarads multiplied by 10 volts. So it's going to be 10.4 microcoulombs. Okay, because the micro is going to stay. Yeah, so that would be the amount of charge on it. And regardless, because it's in series, we know that like this 1.41 is in series with the rest of it, and all of them together have a charge of 10.41 microcoulombs on them. So all of the series components that make up this entire equivalent capacitor have to have the same charge, assuming they're in series. Like the two parallel things, they're going to have different charges in them, but the equivalent between those two is going to have the same charge Q of 10.4 microcoulombs. Okay, so here, so the above solution is good. However, mention of the fact that all series capacitors have the same charge on them would be good to Yeah, it would be good to make the calculation more clear. Awesome. Okay, so I'm kind of running out of time for now. Let me switch over to my cam real fast. So those are all the questions that we have for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring the notification bell below. If you're interested in submitting your own questions, please visit the video links in the description, and remember to leave a like and a comment if you enjoyed the video, and if you really enjoyed the video, share it with your friends. This has been Millan from OneClass, and I hope to see you again soon. And don't forget, physics, always a fun time. Take care. Have a good day.